Right. So we're going to take advantage of these Friday office hours to maybe make some little quick videos about for homework help or for sort of flipped classroom stuff. So today we're just going to do some homework help. Some of you stayed after class to go over some of the homework from week 1 that you should roll over into week 2. So this is not an example of exactly a homework problem, but this relates to number 3 from week 1. So I'm just going to kind of whip through this quickly and then you can watch it as much as you want. So here'd be a sample of a problem where I'd ask you to do lots of things. To determine the charge on the metal, to determine the coordination number of the complex ion, and to draw the structures. In this case, there's going to be 2 different possible structures, but right away, some things that you also want to know, a lot of this is the symbols here. So when we put this in brackets, what's in brackets is the complex ion. So in this case, we have to put something on the outside to show the counter ions. Now these can be confusing. These are just spectator ions that are needed to balance the charge of the complex ions. I don't want you to overthink this. These are not part of the structure. They are there just to balance the charge. So that you know from Chem 1 that Cl, when it's an ion, is Cl minus. Chloride has a -1 charge. There's 2 of them. That means that the complex ion itself must have a +2 charge. Now you should be kind of set to go. You look up on your table or you just know ammonia does not have a charge. Water does not have a charge. Okay? Therefore, copper must have a +2 charge since the whole thing is +2. Now, if this was fluorine with a -1 charge or carbonate with a -2 charge, you'd have to do a little bit of math to figure out what the overall charge is by adding all these up so that it's +2. So this one you don't have to do much work, but sometimes you have to do a little more work. So we're going to ignore these 2 Cl's on the outside right now. We're just going to deal with the complex ion. So we know this. We know that the coordination number equals 6 because there's 6 things hanging off of it. You can look up on the table, monodentate, so we don't have to worry about ethylene diamine or oxalate or carbonate. You can look at the table for that. Now, so when we come over here, we're just going to stick with octahedral for now. So we know octahedral is this structure, okay, where we have these things, and I haven't put any ligands yet. Now we have 2 options for how we can draw this structure. I put the copper in the middle, because that's where it goes. I could put the ammonias here and here, and put them, and then put all 4 waters here in the square plane. That probably would be the thing you would do the most, because that looks like the most symmetric. So then the waters I would put like this. It bonds through the oxygen, so instead of writing H2O, we write OH2. Well, on this side, it looks like H2O. Okay? That would be one perfectly reasonable structure. Another perfectly reasonable structure would be to put the ammonias right next to each other. So instead of 180 degrees apart, now they're 90 degrees apart. That's a perfectly legitimate structure. And then we put the waters here. Okay? We have to distinguish between these 2 somehow. These are called isomers. Same atoms, same number of each atom, same type of each atom, same ligands, same metal, different 3-dimensional shape. Those are called isomers. We call this the trans isomer because the ammonias are opposite from one another. We name them based on the ligands that we can get far apart. When we put the ligands right next to each other, they're close, they're on the same side, if you will, we call that the cis isomer. That's something we didn't get through today in class, but we're going to pick up there on Monday. Hopefully this will help you with your homework.